In the last lecture, we're focusing on the introduction and the application of the Bernoulli equation, right? So I just want to emphasize once more that anytime when you try to use the Bernoulli equation, those four restrictions, for the Bernoulli equation should automatically coming out from your mind, okay? That, you can only using the Bernoulli equation for the steady flow. No friction means, inviscid flow, and in compressive flow, okay? No, this inviscid in compressive flow basically is the title of this chapter. And the last one, important one, is that you only do this along the along a streamline. Okay, anytime you use the Bernoulli equation, you must make sure that all these four conditions are satisfied. Okay, because that Bernoulli equation is pretty simple but very powerful to use. And a lot of times you may automatically just want to use it because it's very simple mathematically. And but if those conditions are not satisfied, the result you got from the Bernoulli equation, may be very wrong. Okay, and this is the thing I want to remind you. And also, keep in mind that Bernoulli equation actually is, we developed from the momentum equation, right? The Euler equation. Euler equation is, the momentum equation. So that, it's indeed, try to showing you that how the momentum is changing, okay, through the, along the streamline. Okay, it's showing you that, okay, this pressure works and the gravity work basically will change the kinetic energy, right? Those, this pressure force and this, gravity force will change your, momentum. This v square over 2, this one, along for the fluid particle along streamline. So this is the way you understand the Bernoulli equation from the view of the, momentum equation. Okay, from the, Newton's second law's way to take a look at this equation. But we already know that, this equation can be also, explained in an energy view, okay? Which means that, we can also looking at this Bernoulli equation as an energy equation. So our task now is try to, also try to derive this, the same form of this Bernoulli equation, but instead of from the Euler equation, we try to, derive it directly from the energy equation. Okay, the energy equation is also called the first law of thermodynamics, right? And so this is what we're going to do here. Okay, let's assume that we create a small control volume. Okay, and this control volume, will be along inside some their boundary. Okay, this control volume is bounded by some streamline. Okay, and this kind of control volume, basically we give them a special name called the stream tube. So basically the control volume, you see that this boundary here and the top and the bottom boundary actually is along some streamline. Okay. And so let's try to apply the first law of thermodynamics into this control volume. Okay, so this will be the full equation thermodynamics, the the integral form of the sort of energy equation looks like. Okay, and the small e here inside this equation is the total energy, right? If you remember what we introduced this in the chapter 4. Okay, and this small u is the internal energy, and v square over 2 is kinetic energy, and dc is the potential energy. Okay, so to simplify this equation, we can make some assumptions. All right. So first, like let's assume there is no shaft work. Okay, so this term is gone. And also that because of that, let's also focusing on the because inviscid flow, so there's no shear force work, because there is no viscous shear stress, right? So this shear work is gone. And also assume there is no other work, so this is gone. And we also assume it's steady state flow, so this partial t term is gone. Okay, and we also assume uniform flow and properties, which means that those the thermophysical properties, okay, they are constant. okay, across the whole flow field. Okay. So with all these assumptions, okay, if you look this equation, energy equation, so the only thing left is this term Q dot. What is Q dot? Q dot is the rate of heat transfer into this control volume from the outside. Okay, and then this term here, and what is term? This E plus PV. This small v is not velocity, okay? This small v is called the specific volume. Actually, this small v is 1 over rho, okay? And this E plus PV actually is this is also called enthalpy, right? So this term here actually is the net flow rate, net rate of the flow, enthalpy flow into this control volume. Okay, so because you need to integrate on all the surfaces, right? So this is this is small h, this is enthalpy, okay, times this is V dot dA. Okay, so that basically is the net for this enthalpy flow into this control volume. Okay, and so because we only have these two terms, right? And also we assume uniform flow, which means that the velocity profile at this inlet 1 and outlet 2, is uniform, the velocity profile. So that you can change this integration into the summation sign. Remember what we learned in that earlier, okay? Because we assume uniform velocity, okay? So keep this in mind, so we can rewrite the energy G equation in this way. Okay, so this is the enthalpy flowing in. This is not the enthalpy, okay? This is the enthalpy, but here we also add the kinetic energy and gravity. So this is like the total energy flowing in, and this is total energy flow out, and this will be the heat transfer. Okay, and again, okay, if we apply the continuity equation, the mass conservation, okay, we can knowing that this term here and this term is here, they are same because they are all equal to the same mass flow rate, right? Because this is rho V1 A1, right? This is rho V1 A1 at this part 1, at this inlet 1, and rho V2 A2 at this inlet 2. They have the same mass flow rate due to the mass conservation. Okay, let's denote that this mass flow rate, okay, is m dot. Okay, and so we can write this two term here as this simply as this way as m dot, and also that let's write this q dot a little bit that to rewrite this q dot change, assume that the change of this, because q dot is the change of the q due over the time, right? This dot means that ddt, right? The rate over the time. So we can do a chain rule, okay, so that we can also relate this q dot as this delta q dm over dm dt, and this dm dt again become m dot. Okay, so we can also write this q dot as this delta q over dm times m dot. Okay, so substitute this one and this one, this one into here, and this one q to q dot here, and your this energy equation will become into this one. Okay, and we have m dot here, and because m dot is a constant, right, and it's non-zero constant, this mass flow rate from the continuity, right? So you can also remove the m dot. Okay, so the only thing left will be this one. Okay, P1 times V1, large V1 square over 2 plus GZ1 equal to P2 small V2 plus large V2 square over 2 plus GZ2 plus this U2 minus U1 minus this change of the Q over the mass dm. Okay, and this V1, V2 here, remember that this is the specific volume is equal to 1 over rho, right? And let's also make the assumption number 6. Let's assume the incompressible. So which means that this V1, V2 is specific volume can be just equal to the same 1 over rho because rho is constant. Okay, so that your energy equation will be writing this way, right? Just change the V1 equal to 1 over rho, right? So your energy equation will look like this way. And you know when you see this equation, you will see that this is very familiar equation looks like, right? Because this is just like the same Bernoulli equation we have earlier, okay? But we have an additional term. And so what's this additional term? So this additional term basically telling you that the change of the internal energy at the outlet and inlet, and then with the contribution of the heat transfer into the system, right? And so let's make the last assumption, okay, assumption 7. So let's also assume that this term equal to 0. And later on we will showing you that why this term has to be 0. Okay. So now you just assume that this term is also 0. Okay. And so your equation will be only left these two terms. P1 over rho plus V1 square over 2 plus GZ1 equal to P2 over rho plus V2 square over 2 plus GZ2. Or in another word, so this one is a constant. So we again, okay, we derived the same form. This equation has the same form of the Bernoulli equation. We derived from the momentum equation. Okay, remember that the Bernoulli equation we derived before is we derived it from the Euler equation, right? That is from the momentum equation. And this equation we derived here, it's not from the momentum equation, it's from the energy equation. It's from the first law of thermodynamics. Okay, so in another way, okay, we derive the same form of the Bernoulli equation, but we derive it from the energy equation, and with different restrictions. Okay, remember that what the restrictions we have for the momentum form of Bernoulli equation, that 4 restrictions, right? Incompressible, inviscid, steadied, along the streamline, right? That is the 4 condition we have for the previous Bernoulli equation. But now for this one, actually we have 7 assumptions, 7 restrictions made. Okay, no shaft work, no shear force, no other work, steady flow, uniform flow and properties, incompressible flow, and the last one is U2 minus U1 minus dq dm equal to 0. Okay, that's why it's meaning that although the equation got the same equation form, but the momentum form and this energy form, they are based on the different restrictions. Okay, and so some restrictions they are same, like this steady flow. Okay, so this is showing on both this energy form and momentum form. So let's denote it here. And in compressed flow, okay, this is also showing in both the momentum and the energy form. And what else? We also assume the inviscid flow, right, in the momentum form. So if you're looking here, so what that inviscid flow means that okay, so this is gone. This is inviscid flow, because that when you have inviscid flow, you have no shear stress, right? Okay, and also like this 1 and 3, this is just like the the external work, right? Basically, in the momentum equation, right? Because that remember our momentum equation, that Euler equation, right? When we try to derive that equation, when we apply that Newton's second law on that fluid particle, right? We only consider the pressure force and the gravity force. We neglect all other force, right? So which means that this one and this one is also gone, because there's no other force in the momentum equation we derive. So all this 1, 2, 3, 4, 6, right? So this is exactly, we can also derive this from, it's likely the same, the same like restriction we made in the previous case. And also for this, also take a look at this condition 5, okay? Because that, because that in this case is, we derive our control volume inside of a stream, so-called stream tube, right? We define our control volume as stream tube, and usually in a stream tube is very reasonable. You just assume that the velocity is uniform, right? So like this one is also satisfied, because that our previous momentum equation when we derive that one, we also along the streamline. Okay, so the only thing left is this one, right? And what is this one? And actually, it can prove that this one will always be true, from the thermodynamics for this is not fractionless, okay, frictionless. This is a typo, okay. So we can always prove that this is true from the thermodynamics for the frictionless and incompressible flow. Okay, so this is always true because that we already assume that inviscid is incompressible, right? We assume that incompressible, inviscid, so that there is no shear work. Okay, so if you have these two assumptions, this will automatically satisfy this one. Okay, so actually, it looks like all this, although we have this although we have these 7 restrictions, but actually they are all can be included in the 4 restrictions we made earlier for the momentum equation. And that's why that, we get the same form. Okay, so you can look at this Bernoulli equation. They are both a momentum equation and an energy equation. Okay, and if you look look this equation as the momentum equation, then this P over rho will be the pressure force, and this G of Z is the gravity force, and this V square over 2 is the change of the momentum. And if you look at this as an energy equation, so this P of rho will be the pressure work, this G of Z will be the gravity work, or the potential energy, or you can say this as the potential energy due to the gravity. And this V square over 2 will be the kinetic energy. Okay, so the same equation, we can derive them from either the momentum equation or from the energy equation. Okay, and they are all share the same restriction, similar kind of restriction: incompressible, inviscid, steady state, no other work, no other force. Okay, and also that remember that the way we derive this equation, we're using this stream tube. So this is similar to the momentum equation that we along the streamline, right? So along the streamline, the last one. Okay, so this is the showing you that we can also have this is the Bernoulli equation, to be able to derive from the energy equation. Okay, this makes this Bernoulli equation become even powerful because Bernoulli equation is already powerful, right? It's the math is very simple. Okay, no integration and differentiation usually you need to do. Okay, but now we also prove that this will be Bernoulli equation will be the only equation you need for this kind of this inviscid problem if it's along the streamline. Why? Because because the incompressible inviscid, right? So the continuity equation plus we only need 3 equations, right? Continuity, momentum, and energy. And now momentum and energy equations are the same equation. So you greatly simplify your problem. You do not need to, instead of you solve like 3 equations, 4 equations, determine that how many direction you have for the momentum equation. Okay, now you just only need to solve 2. One is continuity equation, another one is momentum. This is the Bernoulli equation. That's it. Because Bernoulli equation itself is represented both the momentum and energy equation, right? So you see that how powerful it is. But again, okay, let me emphasize this one small, okay, momentum. This is only true for those restrictions are satisfied, especially inviscid, inviscous, steady, and the very important one along the streamline. Okay, and so this is how we view this Bernoulli equation. Okay, how can we interpret this Bernoulli equation from as an energy equation? Okay, so you may still have the issue for the last assumption, right? Why this is always true for this inviscid and incompressible flow. Okay, on the textbook, okay, we have an example problem to prove it. Okay, so this improvement, okay, is purely from the thermodynamics. Okay, so if you took your thermodynamics, if you already took your thermodynamic class, or if you are taking your thermodynamic class, so you should be familiar with this one. Okay, so I won't emphasize this example problem too much. So basically, just means that it's based on the Gibbs equation from the thermodynamics. It's showing that this TdS equal to du plus rho dV. Okay, and this TdS, this S is the entropy. Okay, this U is internal energy, this rho is the density, and dV, this small v is the specific volume. Okay, because it's incompressible flow. Okay, and so because it's incompressible flow, right? So we all usually just this v is 1 over rho, right? So it's constant. So this is gone. So you only have this TdS equal to du. So this is incompressible flow. And the second one, right? The second one is that we also assume that it's inviscid flow. Inviscid flow, what does it mean? Inviscid flow means that the process is reversible. Because viscous, what the viscous force doing is that it will convert the kinetic energy to the thermal energy, and it's not as an irreversible process. Because like a viscous force, like the friction, right? So when you have the friction force, usually you can change the kinetic energy to the thermal energy, right? Thermal energy, internal energy. Okay, and now because we assume it's inviscid flow, which means that no viscous force. Okay, so that in these cases, okay, so this TdS can be just written as this, delta Q over dm. Okay, then that's why if you replace it here, you see we're showing it here, U2 minus U1 to delta Q over dm. Okay, so this example from just showing you that if you have this frictionless and incompressible flow, this will be automatically satisfied this condition. Okay, so this is this is the things you need to know. And so to further understand this Bernoulli equation as an energy equation, okay, we also have another example problem. Please read this one first. Okay, so for this problem, okay, basically we have a larger tank of water, right? So we call it a water reservoir. And so the water is flowing out through a small nozzle, okay, and the cross-sectional area of this small nozzle is known. And the special thing is that we apply, a heater surrounding this nozzle, okay, and we know the power of this heater. Okay, the power is 10 kilowatt. Okay, basically means, and also that we know that this heater is well insulated outside, so which means that all the heat generated inside this heater will go to the fluid. Okay, so the question is asking us is that what is the temperature rise for the fluid? What's the temperature difference between this 0.4 and this 3 and this 0.3 or 0.1? Okay, so so this problem immediately involves the temperature, right? So we know that the energy equation will definitely we are going to use it. Okay, and so we will using this one here, and also that for this problem we assume that it's steady flow, inviscid flow, incompressible flow, and also that if we write this point, right? So if we know this 0.1, 0.2, 0.4, so we can assume that this 0.1, 0.2, 0.4, and even this 0.3. Okay, maybe we can just draw some streamline to some point, like this point is 0.3. We can assume that all these 4 points, they are along the same streamline. Okay, the last one we can assume that they are uniform cross-sectional area, like the velocity profile here, is same velocity. Okay, and the equation will be involved will be the continuity equation here. Okay, and the energy equation here, because that we need to involve the change of temperature, right? Because that although the Bernoulli equation itself won't give us temperature. Okay, so anytime you have the temperature, you have to use the full energy equation. Will be here, and also the Bernoulli equation we can use to supply the momentum equation. Okay, and why Bernoulli equation you can use for momentum equation, because that four conditions satisfy this one, this one, this one, and along streamline. Okay, so you have all these four equations, all these three equations to use. Okay, and for the energy equation, we do the similar simplification. So this no shaft work, no shears work, steady state. So the only thing left is this one, this one. Okay, and so what I will do? So we can rewrite the energy equation as this form, because this is the only term left for these two terms, and because that is uniform flow for the between point 1 and 2, right? Between this point 1 and 2 here, before heating and after the heating. So we can change this integration to this summation form. Okay, and again, this one we replace this one and this one as m dot. Okay, and this q dot value is known. Okay, and because that this q dot is just equal to this 10 kilowatt. Okay, and so the question asking, I think we have so first is asking asking for us for the the temperature increasing, right? So this q dot is known. We know that the q dot will be equal to and also okay, this is q dot is known. Okay, and m dot is known. M dot we can calculate it. Do we know the m dot? Let me double check. Okay, we do not know m dot yet. Okay, so let's forget about it. We do not know m dot, and u2 minus u1 we leave it here. Okay, and so I also have these two terms here for the energy equation. I also have these two terms here, and these two terms will be equal. Why? Because this is from the momentum equation. This is from the Bernoulli's equation, right? So we know this term and this term should be cancelled out, right, from the Bernoulli. So the only thing left equal to will be q dot equal to m dot times u2 minus u1. And u2, u1 is the change of the internal energy, and then we can calculate it as this one, C times T2 minus T1. C is the specific heat. T2 minus T1 is the temperature rise, between the 2 points. So you substitute this one into here. Okay, so this is the temperature jump. T2 minus T1 equal to Q dot over M dot C. Okay, and now the question is this: we do not know M dot, right? We know Q dot, we know C, right? C is the specific heat of this fluid. We do not know M dot. How will we calculate M dot? Right? So how we calculate this M dot here? So if you look at this problem, so what's the last condition we didn't use yet? Is this one, this depth, right? So what is M dot here? Because this M dot we are asking is the mass flow rate inside this nozzle, right? And because this nozzle's cross-sectional area is a constant, so M dot for this one, M dot at this point 1, M dot at this point 2, M dot at this point 4, they are the same one. Okay, and to know the M dot, and because we know the cross-sectional area, right? So we just need to find that what's the uniform velocity, right? Because velocity is same cross-sectional area, right? And M dot is same. So the velocity at this 3 point is also same. So we just need to find what's the velocity at this 3 point. And this velocity can be found from this depth here. And again from the Bernoulli equation. Why? Because at this point 3, there is no v will be 0, but with this gz with this value, okay, and this PO rho is just here is just atmospheric pressure, right? And then we can calculate the maybe let's say using the point 4 as an example. This point 4 is outlet, the outlet of the outlet of this flow as a nozzle outlet. Okay. So at this nozzle outlet, we can calculate their P again will become atmospheric pressure, right? As outlet over rho plus V squared. This V we do not know as 0.4. And GC, okay, and Z here, let's assume Z here equal to 0, and Z here will be 10 feet. Will be so will and this value here at 0.4 and this value at 0.3, that should be the same. Okay, so we just do that. Okay, and this Z3 minus Z4 will give you this 10 feet. And this P3 over rho, P4 over rho, they cancelled because they are all the atmospheric pressure. Okay, and this V3 equal to 0 because it's a reservoir. There's no fluid velocity there. And you can calculate V4. And then after you know the V4, you calculate M dot. M dot is just rho V4 times V4. And this M dot is the mass flow rate at 0.4. But because it's incompressible, we know that, you know, they are also same at 0.2 and 0.1. Okay, that's the same constant value inside this nozzle. So now we know the M dot. And then you apply this M dot back to this equation here. You can calculate the temperature jump. So you get the temperature jump. Okay, this is telling you that with this heater, you know, and also with this change of this potential energy, so what the temperature will be. Okay, so this is an example to show you that you know how to using the Bernoulli equation for energy problem. Okay. Any question here so far, guys? No question? Okay, so let's continue. And so this Bernoulli equation, right? So let's go back to look at this Bernoulli equation again. Okay, because we have this Bernoulli equation P over rho plus V squared over 2 plus GZ equal to constant, right? So this is Bernoulli equation. And let's rewrite this Bernoulli equation, just divided by this G on the both time on the both side. You know, divided this gravity on both sides. So we can write this one. So basically you are P over rho G plus V squared over 2G plus Z equal to a constant. Okay, let's denote this constant as H. Okay, so what is the unit for this H? This constant H will be along the streamline, right? So basically that so you will have this constant value H for different streamline, right? Along the same streamline, you have the same constant H for this quantity here. So what's the unit for this H? So H, yeah, this H and this Z should have the same unit, right? And this Z is the elevation. So this H will have also the unit in length. Okay, so we call this H called the total height in the hydraulic, you know, hydraulic, you know, engineering. We call it H called the total height. Okay, they call it total height of the flow, and basically it means so what's the physical meaning of this H? Because they are, you know, their unit is the length, right? Like in meter or feet, right? So what's the meaning of it? It just meaning that if you have a flow, and if you calculate what's the overall total mechanical energy, what's the mechanical energy, will including the pressure work, including the kinetic energy, including the, you know, gravity potential energy. Okay, and if you try to convert this total mechanical energy, you know, into an imaginary cases that just like a flow, just like your flow, you give a height, give a elevation, you know, like you know, you have a flow has no motion. Okay, like you put a flow like a put it at a very high, you know, elevation, like with a tank, and this elevation is H. And so that because the velocity for the flow inside this tank is no velocity, and also let's assume that, you know, the pressure work is almost the, you know, in this tank is also like 0. Okay, like, you know, this is like a vacuum cases, a vacuum tank. Okay, not vacuum tank, it's like a, you know, 0 pressure, you know, something like imaginary, you say. Just like, you know, you convert all this mechanical work into a potential into a same kind of fluid, but with but it only process the gravity potential energy. with age. Okay, just like you convert everything, all the mechanical energy to a fluid like only contain gravity energy, potential energy, gravity potential, and this fluid like you have to elevate it to this length h to let it has the same kind of gravity potential energy, comparing to this total energy. Okay, that's why we call it height, because we're moving up, right? Okay, so this is just some some physical some terms we use in the hydraulic engineering. Okay, and so this h will be, we call it the total height, is in the units of length. Okay, and again, okay, because that Bernoulli equation is valid for each streamline, right? So you will, for each streamline, you will have their own value of h. Okay, and so with this one inside, okay, with this in mind, okay, we can also, in another way, okay, to represent the Bernoulli equation, because that for this Bernoulli equation they are constant, right? So this one is constant. So we can also try to represent the Bernoulli equation graphically. How we do that? How we do that? What we can do is that we can try to, if you have a if you want to draw the lines, right? We can define these two concepts here. The first concept is called the energy grid line, in abbreviation is EGL. Okay, so what the energy grid line means that this EGL is just defined as this P over rho G plus V square over 2G plus Z. Okay, so that if you have a if you have flow field, right, you can try to draw a line that for different EGL value, like I have this EGL equal to 1, and then you have draw another line called EGL equal to 2, whatever. Okay, so you can use this way to represent the flow field. And what's the meaning of this EGL? It's basically meaning that it will include it's better to look at the energy way, right? It's including the total mechanical energy. It's including the pressure, work, gravity, and kinetic energy. Okay, and sometimes we are not interested in the kinetic energy. Okay, so in that case, we can define the second kind of concept, which is called the hydraulic grid line, HGL. Okay, in this case, we only including this term and this term, the pressure work and plus the gravity potential. Okay, so now you have two different. You can also draw, when you want to visualize your fluid, right? You can also draw the lines, like for different HDL value. And why we need HDL? Because that usually the HDL itself is not very useful. Okay, the HDL itself is not very useful because that as you already can see that this EDL is useful because that is including all energy, but HDL is just like you remove the kinetic energy. Okay, so this is just like an auxiliary line which help you to find the velocity. Why? Because that if from the definition of these two, you know that it is EGL minus HGL equal to V squared over 2G. Okay, so basically that the important thing is not this HGL. Okay, the important thing is that this EGL, and this HGL is only used to help you to find what the velocity. Okay, so if you have a graph, okay, so if you have a flow field, you have the first drawing like in this EGL, and the second one you draw some curve like this HGL, okay, and then you can calculate velocity from these two graphs, because that is the value difference at each point will give you the velocity at that point. Okay, so this is the so-called energy grid line and the hydraulic grid line. So to further, interpret this, this graphical method is like, we can use an example to showing you. Okay, and so let's use this one as an example. This picture looks a little bit complicated, but let's study it one by one. Okay, little by little. So again, okay, so this is again that you have a nozzle, okay, so that the flow is flowing from a large fluid reservoir, and so let's denote several points here. The point one is that this is the upper surface of this tank, water, the fluid inside this tank, okay? And we also that this point two, right? Because that if you take a close look of this nozzle, okay, you can separate this nozzle in three parts. This part here and this part here. Actually, the part here and the part here, the nozzle has the same cross-sectional area. The constant area is not changed. But for the region between here and here, you see that this nozzle, their cross-sectional area is changed. This is has larger cross-sectional area here, but with a smaller cross-sectional area. So we denote this beginning, location of at 2 and this end location at point 3. And this point 4 is still again is this nozzle exit. Okay, and again we assume that this is a steady flow, inviscid and incompressible. Okay, and let's also assume that this we can draw a streamline here, right? We could definitely the flow here can be from a streamline. Let's also assume that it's 1, 2, 3, 4 points are all along the same streamline. Okay, so now let's take a look at this EJL and AJL lines. Okay, so first let's take a look at the EJL line. So what is EJL line? EJL line is that it including the same, including all the kinetic mechanical energy, right? And so if you look at, so the point 1 here, so what is the total mechanical energy? Will be this pressure, atmospheric pressure over rho, right? Rho over rho g, and then that's it. Sorry, not that's it. You also need to include in this potential energy, like assume that it's plus this c1, because velocity is 0, right? And then similarly for this location 2 here. Okay, because it has a velocity, right? And so this will be that HGL value will be what? Will be P, the pressure at this point over rho g plus the V2 square over G plus this Z2. And similarly for the others, point 3 and point 4. Okay. But because we assume that this is incompressible and inviscid flow, right? So do you have any loss of this total mechanical energy? You didn't lose any mechanical energy because it's frictionless. There is no viscous force, right? There is no friction. So there are this energy here, again, the velocity is only because this potential energy is converted to the kinetic energy, and so on. Okay, so their total energy, if you added this potential energy due to gravity, add this total energy, add this pressure work, altogether, all these 4 points, they will have the same EJL value, same energy green line. Why? Because their total energy is same. They didn't lose any energy to other form, right? There is no any mechanical energy will be converted to other kind of form of energy, right? They are all the same kind of mechanical energy. The only difference is that some potential energy is converted to the kinetic energy, but both potential energy and kinetic energy, they are all included inside this mechanical energy already. Okay, that's why is that when you try to draw this energy grid line, right, this dashed line here, they are horizontal line. Because at this 4 location, point 1, point 2, point 3, point 4, they have the same total mechanical energy from the energy conservation. Because this mechanical, you have no transfer of mechanical energy to other kind of form. No viscous force. If you have the viscous force, then this will not be a straight line. Why? Because the viscous force is like the friction. Friction can convert your mechanical energy to the thermal energy, internal energy, right? So that's why that is EJL line. You see it's a horizontal line. And then now let's look at this HGL line, hydraulic grid line. And from this here, you know that the hydraulic grid line is closely related to the velocity, right? So you can see that you can rewrite this one as HGL will be this EJL minus V square over 2G. Okay, so which means that the larger the velocity, the lower of the HDL. Why? And when this EDL is constant. Okay, remember that this EDL is constant for that 4 points. Okay, so if you want to determine that this HDL line, you only need to determine from the velocity. Okay, so here, because velocity is 0, so your HDL line and EDL line, they are coincide at the same point because V equal to 0. And then to this point 2 here, okay, and because this potential energy, will convert to some kinetic energy, so you will have V2 velocity. We have a velocity here, right? And so actually, with this V2 square, you will basically velocity will be increased from 0 to this V2. And then that's why you see this HDL line actually is declined, right? Because that the larger the V square, the larger the velocity, the smaller the HDL, right? And this declined length, right? The value change from this EDL is just this V square over 2G, okay? And that's why is that you see this blue line is this HDL line. Now it's has this depth length, decrease from this EDL, and this value will be V2 square over 2G. Okay, and then this is the point 2, right? Let's look at the between point 2 and point 3. And now because that this cross-sectional area of this nozzle is reduced, right? Because we know this is m dot equal to rho times v times a, right? And because that from the continuity we know the m dot has to be constant. And when you try to reduce this cross-sectional area, right? Cross-sectional area here is larger, cross-sectional area here is smaller. When you try to reduce cross-sectional area, so what happens? You have to velocity will be increased, so that they can match the same mass flow rate, right? So basically, from the point 2 to point 3, you have a increase of the velocity. And again, okay, you increase the velocity, you further decrease the HDL, and that's why that you see this HDL line, this blue line, further reduced. Okay, let's assume that it's reduced to here. This is point 3, and then between point 3 and point 4, again, now there's no cross-sectional area change, again, right? And then no cross-sectional area change, no velocity change. So this point 3 and point 4 has the same velocity, so there's no this HDL line change anymore. Okay, that's why you when you look at this blue lines, right? So they are looks like this way. And if you only taking a look at the last point, right? So this difference, this HDL line difference, this length here will be just V4 square over 2G. Okay, so this is like in the hydraulic engineering, right? How we use this kind of how we draw this EDL line and HDL line. Okay, so some conclusion we can make here, okay, because we assume this flow is inviscid and incompressible. Okay, so usually for the inviscid incompressible flow, because there is no loss of energy, okay, so the EDL line is always constant, right? So you see a constant line here, but this is only true for this incompressible inviscid flow. Okay, and HDL line will keep it lower, right, if this velocity is increasing. So this is second conclusion we have here. All right, so this is just some concept, okay, from based on the definition of the based on the Bernoulli equation, okay, we can further have this kind of this EDL and HDL way to to represent the problem graphically. Hydraulic problem. Okay. Any question here? No question? Okay, let's continue. And remember the Bernoulli equation, right? We previously developed either from the energy equation, energy V, or from the Euler equation. Okay, we all assume it's a steady state flow. Actually, it's possible that you also derive the same kind of Bernoulli equation along the streamline for incompressible inviscid flow. Okay, but for an unsteady state flow. Okay, remember that four condition we mentioned before, right? The incompressible, inviscid, steady flow along a streamline. Okay, now let's just make it three condition. Remove that steady state flow. Let's also try to derive the Bernoulli equation for an unsteady state flow. So it's possible. Okay, and this is the final result. Looks like. Okay, and the way to derive, it's just an option. It's optional for this lecture. Okay, so this section actually, anytime you see I add a star on the lecture notes, okay, that means that this type of content is just an optional content. You do not need this for the exam. Okay, and do not confuse this star, in the lecture note with the textbook. Okay, I know that your textbook also some chapter has that star, but that not necessarily means that those parts will not included in the exam. Okay, only the lecture notes, the section has this star means that is not included in the lecture notes. Okay, keep this in mind. And so this is the way how you can derive unsteady Bernoulli equation. Okay, again just study from the vector form of the Euler equation, and then you times a small ds vector along the streamline, and then you integrate this result on 2 points v1 and v2, 2.1 and 2 along this streamline, and this is with the result. And the only difference is that you will have an additional term for Bernoulli equation, and this additional term is related to the time transient, right? Partial v, partial t ds. Okay, so this is called the Bernoulli equation for the unsteady. This is called unsteady Bernoulli equation, and this additional term here can be interpreted that the work you may require to change the rate of the momentum along the streamline. Okay, and so this is just some introduction. Okay, and you do not need this for the homework or exam. All right, so now we're focusing on a lot of, talking about a lot of, we talk a lot about the inviscid and incompressible flow, right? For this chapter, we see that, for this inviscid incompressible flow along the streamline, we show you that the momentum and energy equation both will collapse, both will lead to the Bernoulli equation, right? And there's one last special form of the fluid we want to introduce a bit, and it's called the irrotational flow. Okay, remember that what we did before is for the condition like inviscid and incompressible, right? And now, what we did before is inviscid, right? And incompressible. Now let's add the third condition. Let's assume the flow is also irrotational. Okay, so the flow is still inviscid and incompressible. Now let's add a new condition. Let's also assume that the flow is irrotational. Okay, what is the irrotational flow means? That means that your angular velocity is 0, omega equal to 0, or vorticity that zeta equal to 0, right? From the previous chapter. And in another word, you can see that the curve of the velocity field is equal to 0, right? This means that the irrotational flow. Okay, and so if you write this from the vector form to the component form, okay, on the rectangular coordinates, irrotational flow simply means this one. Okay, on xy plane, this has to be satisfied. On the xz plane, this has to be satisfied. On the yz plane, this has to be satisfied. And similarly for the cylindrical coordinate, this is the meaning of the irrotational flow. And why we want to reintroduce irrotational flow? Remember that previously when we try to see the Bernoulli equation, right? So Bernoulli equation is work for these two conditions, and then we also know that Bernoulli equation is only valid for the flow along the streamline. Okay, now if we add the third condition, irrotational flow, we can further prove that the Bernoulli equation will be valid not only on the flow, on the direction of the streamline, actually will be valid for any 2 points inside this flow. Let me repeat it, okay? So Bernoulli equation we derived before basically means that for inviscid incompressible flow, steady state, but only along the streamline. Okay, but now if we add this condition, if the flow is also irrotational, actually you can remove that the last condition before, like has to along the streamline, because that in these cases, actually I need 2 points inside this fluid, no matter if they are along the same streamline or not. The Bernoulli equation will also satisfy, will still valid. This is why this irrotational flow is so special, because that if you have this condition here, you do not need to, when you try to use the Bernoulli equation, you do not need to have to along the streamline to use it. Okay, so this is a proof how we can prove that. Okay, again we will start it from the vector form of the Euler equation. So this is vector form of the Euler equation. Okay, and this convection term, we can from that vector operation we can write it into these two terms. And this because that is irrotational, right? So this term should go to 0 because that curve v, right? So the only thing left is here. Okay, so your Bernoulli equation, so your Euler equation can be read in this form. Okay, that v squared over 2. And now instead of you integrating along the streamline, now let's just integrating for an arbitrary infinitesimal displacement along your flow field, dr. This dr, it maybe along the streamline or may not along streamline, is arbitrary. Okay, it's not necessary this dr has to be along the streamline. And remember, you can write this dr as the dxi plus dyg plus dzk. Okay, you substitute this dr in this component form into this equation here, and then you do the integration, and you write this gradient you know in the component form, and you will also again you will approve this. And in another word, okay, it is p over rho plus v squared over 2 plus g. They will be constant for arbitrary dr. This dr not necessarily has to be along the streamline. Okay, so that's why that you are showing you that if your flow in addition to inviscid incompressible steady state, but also irrotational, then your Bernoulli equation will be valid for the whole flow field. Okay, so let's make a summarize here. Okay, so now until what we learn here, right? So if we have this Bernoulli equation in this form, in what condition it will be satisfied? Basically, if I answer this question, I will make it in 2 scenarios. The first scenario will be if the flow is steady state, incompressible, and inviscid, and along the streamline, this will valid. The second scenario, steady state, incompressible, incompressible, inviscid, and irrotational. This will also be satisfied for everywhere. Okay, so now this equation has 2 cases, right? The first one is inviscid, steady, inviscid, incompressible. Okay, this is, and then along the streamline. Right. The second one will be same steady, inviscid, incompressible, but plus irrotational. Okay, so if it's not, so basically, in another word, okay, if the flow is not irrotational, if flow is rotational, then this is only valid along the streamline. Because the first 3 condition, assumption is always assumed is true. Okay, so if the flow is irrotational, this is only valid for the flow along the streamline. If the flow is irrotational, okay, then this will be valid everywhere. Okay, keep this in mind. Okay, any question here so far, guys? No, keep it, now you should in your mind, right? So that what condition this Bernoulli equation can be used, right? So this is the most important things of in this chapter. So keep this in mind. Okay, the two conditions. Okay, the 3 conditions is always true. Okay, steady state, inviscid, and incompressible. The last one, it depends on cases. If it's a rotational flow, it's only valid on along the streamline. If it's irrotational flow, it's valid everywhere. Okay. And so let's continue. You know that for the irrotational flow, right? Because that irrotational flow basically means that the curve of the velocity field equal to 0. So with this in mind, okay, it's for irrotational flow, it's possible, okay. So we can introduce a new companion function, which is called the potential function phi. Okay, I will explain that why we can define it. Okay, usually we define the velocity v as a negative gradient of phi. So if we can define, so if we can represent our velocity field in this negative gradient of phi, okay, in other words, okay, in the rectangular coordinates, that means that u will be equal to this one, v equal to this one, w equal to this one, or the cylindrical coordinate means that vr will be this one, v theta will be this one, vz will be this one. Okay, so if you can represent your v velocity as using this potential, so if you can prove that there is a potential function phi exists for this velocity field in this way, then you know this irrotationality, this curve v will be always equal to 0. Why? Because that this is always true. This, if you do a curve over a gradient of scalar field phi, okay, so it's always equal to 0. This is a mathematical identity, fundamental identity. Okay, for any kind of for any kind of a scalar function f, and if you first do a gradient on it, and then this gradient phi will change it to a vector, right? And then you do a curve of this one, it will always equal to 0, no matter what. Okay, and that's why is that you know when you have this irrotational flow, it's possible for us to find a potential function phi, like to satisfy that this velocity phi can be a negative gradient phi. Okay, so in another word, so if flow is inviscid, incompressible, and irrotational, you can define a potential function of the flow field in this way. Okay. So why we want to do that? Because it can greatly simplify your problem. Let me show you. Okay. So let's assume that you have two-dimensional incompressible and irrotational flow, and also that because irrotational flow you can define this potential function phi, right? So for irrotational flow, we have this based on the definition of this potential function. We know that u can be read this way and v can be read this way, right? This u here, this v here, and also because that is incompressible. Incompressible means that this is a continuity equation, right? This is incompressible continuity equation. And if you substitute this two here into it, what do you get? You get that this Laplace of this phi equal to 0. So this is called the Laplace equation, second order derivative of phi on x plus second order phi on y equal to 0. Okay, so this is called the Laplace equation of phi equal to 0. Okay, and this equation is special. Why? Because that this we call this Laplace equation is very, you know, very handy. Why? Because that if you take a close look at this Laplace equation, they are a linear differential equation. There are no nonlinear term, right? Because this is just phi. This is just phi. They're not a phi times another derivative or derivative times another derivative. It's a linear term, linear term. So this is a linear differential equation. And if you know the boundary condition for your flow field, right? If you know the phi value at all the boundaries, you should be very easily to solve this problem, solve this equation for the phi. Okay, so you can calculate what the phi as a function of x, y, if you know all the boundary condition. And if you know the phi of x, y, and based on this definition of this stream function, so not stream, potential function, you can quickly calculate what the UV field, right? So in another word, okay, by do this definition of potential function, phi. Okay. Instead of solving that continuity equation, momentum equation earlier, okay, we can just try to solve this equation directly, try to get the velocity field. And this equation is very simple to solve because it's linear. This is why we introduce this potential function phi into this irrotational flow. And again, I want to emphasize that you're only able to do this for irrotational flow. If the flow is rotational, you cannot define a potential function for phi for it. Okay, only define this potential function phi for irrotational flow. Why? Because that this identity here, this is always true. Okay, so if it's a rotational flow, you define a phi, it will become 0. You again get this curve. You can get this curve v equal to 0. So this will violate your assumption. Okay. And you may look like this form, right? This u equal to minus partial phi partial x, v equal to minus partial phi partial y. Looks very similar to the things we defined earlier, right? Like those called stream function. Like their format looks very similar. Okay. So to let us that to be aware of the difference between these two, let's also remind that what's the definition of stream function. The stream function psi is defined in this way: u equal to partial psi partial y, v equal to minus partial psi partial x. You see that it's the difference between psi and phi. Okay, this is partial phi partial x, right? This is partial psi partial y, right? So now you see the difference. Okay, and again, so this is the incompressible flow, right? Remember that you can only define the stream function for the incompressible flow. Why? Because that after you define your stream function in this way, your continuity equation, this continuity equation will automatically satisfy, right? So you can only define the stream function in the incompressible flow. But again, if also let's assume that the flow is irrotational, this is the irrotational condition on the xy plane, right? From here, irrotational, this one has to be 0. Okay, and if you substitute this uv from this psi function into it, you substitute this 2 into here, again, this will lead to what? A Laplace equation of psi. It's showing you that this Laplace square of psi equal to 0. And so what do we learn here? We learn here that if you have these two conditions satisfied, incompressible and irrotational, okay? So any function psi and phi, the stream function psi and the potential function phi, will all of them will be satisfied Laplace equation to represent a possible two-dimensional incompressible flow. Right? And so this kind of flow, this incompressible, inviscid, and irrotational flow also is inviscid, okay? Inviscid is always true here, okay? If you have flow, it is inviscid, incompressible, and irrotational flow. Okay, we usually call this kind of fluid perfect fluid or potential flows. Why? Why they are perfect fluids? Because that their governing equation is linear. It's just a Laplace equation. We can solve it very easily. Okay, so that's why we call it perfect flow. Perfect flow basically means 3 things, okay? Incompressible, irrotational, and inviscid, okay? I forgot to add it here. So if you have 3 conditions satisfied, we call it perfect fluid. Okay, and you remember that from the psi, right? This stream function, we can define the streamline, right? Basically, we know that for each streamline, psi is equal to constant. So basically, after you solve this psi as xy function, and you make it to constant, you can just to draw the streamline on your flow field. Okay, and similarly for this phi, this potential function, if you make it after you solve the result, and if you make it constant, you can also draw so-called the equipotential line. Okay, and you can prove that these 2 lines, okay, they are orthogonal to each other. Okay, so if this is psi 1, psi 2, psi 3, okay, and then your your equipotential line will be, maybe this is the phi1, phi2, phi3. They will be orthogonal. Why? You can prove it from this mathematically, okay? Because this is along this streamline d psi equal to 0, along the equipotential line d phi equal to 0. And you can prove that for the streamline, right, their tangent direction will be equal to v over u, right? And on this equipotential line, their tangent direction will be minus u over v. And you see that this one and this one here, they are negative reciprocal, which means that their direction is 90 degree perpendicular, okay? So this is another thing I want to introduce. And I forgot to show you a figure on the textbook. On the textbook is very useful actually. On the textbook, we also have a figure to summarize all these things, okay? The correlations between phi and psi, okay? And that is the figure. Let me double check. That is table 6.1, okay? So it's a table 6.1, okay? You can take a look at your textbook for it. So basically, it summarizes all these two slides we read here, okay, in a simple table. Like if irrotational and incompressible, you will you get the Laplace equation. If incompressible, irrotational, you get this same Laplace equation for the phi. Okay, try to take a look at that table yourself. It's just a summarize of these two slides. Okay. Okay, so let's have some example problem. Okay, and this example problem is similar to the previous example problem to ask you to calculate the streamline, right? Stream function. And now let's try to calculate the potential function. Now let's assume that we know the potential function. Oh, no, what I'm doing. Let's assume that we know the streamline, okay? Is this streamline? Yeah, so this is size streamline, right? Let's assume we know this streamline. And if we know the flow is also irrotational, okay? So what is the phi value will be to determine the velocity potential, okay? So you from the stream function psi, and based on this definition of stream function psi, right? Actually, you can calculate what the velocity field u and v, right? Because like u will be partial psi, partial y, right? V equal to minus partial psi, partial x. And after you calculate the uv here, and again you go back to the definition of the potential function phi, because u equal to this one minus partial phi, partial x, v equal to minus partial phi, partial y. And then you do integration one by one, you can calculate the phi, okay? So first so from here, you can calculate what the phi value will be. You first you integrate on x, and then you can integrate on y. And then you know that, your potential phi value will be this way. Okay, so this is a very simple example problem, just showing you that, if you know the psi value, the stream function, okay, you can calculate the velocity from it, and then you can again calculate the phi potential, velocity potential from the UV value. Okay, and keep this in mind how to do it. Okay, so here we just introduce the very fundamental things for the irrotational flow. Okay, actually the topic for this irrotational flow is a big one. If you have chance to take the graduate class in Stony Brook, actually we have we have individual graduate course. I forgot what it is. It's MEC 509 or 506. I forgot. Okay, the whole class we are talking about the solution of this irrotational flow, and that class is called the perfect flows, perfect fluids. And why? Because that we already know that if we want to get the UV field, right, velocity field, we only need to solve this Laplace equation, either for phi or for the psi. So that we can get very easily to get the analytical solution for different kind of flow problems, because this equation is very simple to solve. if we know the boundary condition for C and phi. Okay, some example problem result can showing you like this. Okay, this is definitely the optional. Okay, if you read your textbook, there is a whole section for that. You know, so those called elementary flows, like a very simple structure of fluids is incompressible, inviscid, and irrotational. And by solving those Laplace equation for phi or psi, okay, you can get the result. And this is the flow field, like if you have a source, so-called source of the flow, basically like you have a source fluid source at the middle, so that the flow is coming out from this source, okay, and so this is like you know, the result like called you know, circular flow, okay, like if the flow is circulating, okay, and what the calculation result will be, the phi and the psi, okay. So there are more kind of, you know, solution for this different kind of elementary flows, okay. How to solve it just pure mathematically, okay. Just give the different boundary condition, you know, you can solve those psi and phi from those two Laplace equation. Okay, another thing we want to mention is that because that both of the fluid, right, both of the equation, that psi equation and the phi equation is Laplace equation, right, is linear equation, is linear differential equation. Actually, you can using the method of superposition. What the superposition means that if your problem is linear, okay, if your problem is linear, you can decompose a very complicated problem into several simple problems and just add it together. What does it mean? I think I gave this example before, right? So if you want to calculate, for example, if you want to calculate flow like this way, okay, you have a flow between the two plates, and then I put a cylinder inside here, okay. And if I want to calculate the result for this one, actually, if we know that it's inviscid, incompressible, and irrotational, in another way, we know that it's a perfect flow, okay, perfect fluid, which means that you know, the problem is linear. So instead of solve this problem, I can just solve that the first problem, that a flow between the two plates. I calculate this psi and phi for this problem first, and then I just solve the problem psi and phi for another problem, like the flow over a cylinder. The result, this one will be just equal to this result plus this result. So this is called the superposition. And you know, on the textbook, right, you have a table that showing you that the different elementary flows, showing the results. And if you find a flow problem which can be combined with some linear combination of these elementary flows, you just add them together to get your solution to fit for your problem. Okay, so this is the meaning of the superposition meanings. And remember that this superposition is only valid for the linear problem. Okay, the reason you can do it is because that those Laplace equation for the psi and the Laplace equation for the phi, they are linear. Okay, and if it's the original Euler equation, original Navier-Stokes equation, you won't be able to do that because that you have this v dot grad v term, right? That is, you know, u partial x term. You have those kind of things. This is convection term, or this mu partial square u partial x, not this one. Okay, this term. This is a nonlinear term because you have u times another u, you have v times another v. You won't be able to do that because the problem is nonlinear. Okay, and you cannot use the same superposition method for those Euler equation for Navier-Stokes equation. No. All right. Okay, so here I finished the this chapter 6. Okay, and I think we have 3 weeks class left. Okay, so we'll, you know, next, you know, after the midterm, Friday's midterm, we'll continue for the chapter 7, which will introduce the method of similarity. Okay, non-dimensionalization and the similitude, and after that we have chapter 8 and chapter 9. Okay, and any questions, guys, so far? No question?
Professor, what chapters are the exam going to cover?
Chapter 4 and 5. So this is chapter 6, right? So chapter 4 and 5. Okay, I will send an announcement today. Okay, for the to what we'll cover for the midterm. It's chapter 4 and 5, and So all the content in this chapter 6 is not included. Okay.
Okay, thank you.
No problem. Any other question, guys?
And just to confirm, we're allowed a cheat sheet for this test too as well, right?
Yeah, it seems everything is same as previous midterm. Everything is same. Okay, so if there's no question, and just do your best for the Friday's midterm. Okay, do not forget to attend it. And for new homework, right? Because we finished this chapter, we will have a homework for this chapter, but I will give it next Monday. Okay. So that you won't take your time for the midterm.
Professor?
Yes.
For this upcoming midterm exam, would the homework problems for chapters 4 and 5 be good practice?
Sorry, will the chapter 4 and 5 homework for what?
The homeworks 3 and 4, would those be good practice for the exam on Friday?
Homework 4 and 5?
Like the homeworks for the chapters covered on the exam.
Yeah, chapter 4 and chapter 5. Yeah, it will be there. But the problem you have won't be as complicated as the homework problem, because that some homework problems require you to a lot of time to calculate it, right? And we only have 1 hour 20 minutes. So similar to our first exam, a lot of problems will be just for the concept. Only a few problems for you need to do the calculation, and also that the calculation will be the simplified version of your homework problem. Because that I won't like a design problem like you to need to take like 30 40 minutes to finish one problem. That we cannot do that for this 1 hour 20 minutes exam. Okay, so will be some will be like 4 5 multiple choice problem you need to do the calculation, but it will be won't take you won't need you to do a lot of math calculation. Okay.
Okay, thank you.
All right. So if there's no problem, I won't be able to see you on Friday. But just do your best for the exam, and if you have any issue during the exam, like write me an email immediately. I will be there. And also that if you have any question, I also have my office hour on Wednesday. Okay, you can go there to ask me. All right. So no problem. I just finished here, and I'll see you guys.